All right, welcome to the last lecture in this unit. It says, what do you mean it's not 100%? The quote we have here, I knew I could control one thing, and that is my time and my hours and my effort and my efficiency. So, looking at our learning goals, what we hope to accomplish, students will understand some of the factors that restrict the experimental yield, and students will be able to calculate the percent yield. So when we're looking at this, it's really all about percent yield in this lecture. What we already know coming into it, reactions are limited to the amount of reactants, and so we have a limiting reactant, we have an excess reactant. Running out of one of the reactions halts the reaction. So when we run out of the limiting reactant, it stops the reaction, we stop producing product. And then all reactants must be present for the reaction to occur. So we actually have to have the reactants there for everything to take place. What we learned in the lab, there are times when you won't get as much product as the equation in math tells you that you should. Very few chemical reactions are 100% complete. Very few of them. Normally we're going to get close, but we're not going to get 100% on every single one, and some are far less than that. So nobody's perfect. Reactions almost never reach 100% of their possible yield, and that just comes from experimental error and things like that. So what reactions depend on many factors: temperature, pressure, and volume, if there are catalysts used, a medium, number of reactants, a concentration, a number of products, a concentration. So there are a lot of things that go into, is the reaction going to get close to 100%? So let's jump into really an example here. It's really the best way to do this. And so let's talk about this first example. So in the first example, it says that doctors are in desperate need of 2-acetobenzoic acid, and a chemist has 2.5 kilograms of salicylic acid and 1 kilogram of acetic anhydride. What can be done to maximize the yield of the reaction? So when we're talking about maximizing the yield of reaction, things that we can do, if we want to make sure the reaction goes to completion, increase the temperature. By increasing the temperature, we're going to increase the amount of collisions that happen, and so therefore you have a greater likelihood of having 100% or getting close to 100% yield. Decrease the volume. By decreasing the volume, that means that we're pushing the particles closer together, and again, more collisions will take place. Because remember, chemical reactions are all about the collisions and all about the reactants coming into contact with each other. If they don't come into contact with each other, they're not going to react. And so by decreasing the volume, we're increasing the likelihood they're going to hit each other. Increase the concentration dissolved in solution. Again, what does that do? It makes it more concentrated and more likely to run into each other, and use a catalyst. What does a catalyst do? It speeds up the reaction. It gives a place for the reaction to occur, and it's just bringing those particles together. And so those are some of the things that we can do to increase or get close to the maximum yield, making sure that all the atoms and all the molecules get close to each other, touch each other, and actually have a chemical reaction. Our next example, it says, explain the role of sulfuric acid in the reaction below. So when we look at sulfuric acid, when we see this, it should be written over the arrow. So H2SO4. And so this should be written above the arrow. Anything that's written above the arrow, that is a catalyst. And when you have a catalyst, remember, all that does is that sulfuric acid, it'll remove the OH from the molecule and form a positive carbon. And so the carbon and hydrogen when we're talking about it in here. And so what it does is it removes it, and it just makes the reaction happen faster. It gives a place for the reaction to occur, and it just helps catalyze the reaction, makes it where it actually, that HCl will come into contact with everything, and that those reactions will actually touch each other, and that helps the reaction take place. And that's what a catalyst really does. A catalyst just gives a place for the reaction to occur, which helps speed it up. It doesn't actually have a place in the reaction. It's not going to be in the reactants for the products, but it just speeds up that reaction. So when we're talking about percent yield, it's a measure of efficiency of a reaction. And so how efficient is the reaction when we're talking about in the reaction? Are we going to get close to 100%? Are we really far away? Is it a very efficient reaction or not? So both of these reactions can produce sulfuric acid, but the second one is much more efficient. So when we're looking at the second one produces a greater percent yield, so it's more efficient at producing sulfuric acid. The one above doesn't. And so that's really what percent yield is it's looking at the efficiency of the reaction. So when you calculate the percent yield, stoichiometry always starts with a balanced chemical equation, always. The second thing we have to have is we have to identify the limiting reactant. And then we have to calculate the maximum amount of product that could be produced. And that's the theoretical yield. And that's the last thing that we learned in the last section was the theoretical yield, how to calculate it. And then we have to measure the mass of the product that's actually produced. And you do this in the lab. So when you find the actual product, that's what's actually produced in the lab. And then we use the formula, percent yield equals the actual divided by theoretical times 100. That'll give us our percent yield. Very simple equation. The actual comes from the lab. The theoretical comes from calculating it from the limiting reactant. So make sure that we're paying attention to that. So let's jump into an example. When we're looking at this, it says that 1,500 grams of zinc is available to react with 200 grams of copper 2 sulfate. This resulting yield of copper is measured to be 70 grams. So we measured this in the lab. What is the percent yield of the reaction? So in looking at this one, we can look at it and we have 1,500 grams of zinc and we have 200 grams of copper 2 sulfate. So when we're looking at this, the first thing that we have to have is a balanced chemical equation. And the first thing we have to do before we balance it is we have to actually write the equation correctly. So let's go ahead and let's start with that. And I'll give us our balanced chemical equation. So we have 1 mole of our copper 2 sulfate reacts with 1 mole of zinc, and it produces 1 mole of zinc sulfate plus 1 mole of copper. And so here's our balanced chemical equation of what we have. From here, after our balanced chemical equation, we have to identify what the limiting reactant is. And so when we're looking at this, we want to look at each one. And so when we're looking at the big thing here, we see there's a huge difference in this. There's 200 grams of copper 2 sulfate and there's 1,500 grams of zinc. Now, not every problem you'll get this. Some of the problems will be a little bit closer together. Since everything's at a 1-to-1 ratio, when we're really looking at this, it's just an enormous amount of zinc. And so what we can say is that when we're looking at the big, gigantic ratio between those two things, we can really say that copper 2 sulfate is going to be our limiting reactant. Because there's the reason why we can do this, and it's kind of a time saver, when we're looking at it, we see that it's a 1-to-1-to-1 ratio. And there's just an enormous amount of zinc there. And so the 200 grams of copper 2 sulfate is going to be our limiting reactant. But let's just check and make sure. So when we do this, since we have grams of copper 2 sulfate, we got to have the molar mass of copper 2 sulfate. So 1 mole of copper 2 sulfate equals the mass, which is 100, right around 160 grams of copper 2 sulfate. And then we know that there's 1 mole of copper 2 sulfate in one reaction. And so we set this up. We always start with what the problem gives us, 200 grams. We set it up. 160 grams goes on bottom. 1 mole of copper 2 sulfate goes on top. And then it is 1 mole of copper 2 sulfate in one reaction. And we see that the copper 2 sulfate is going to produce right around 1.25 reactions. And then if we look at our zinc, we now have 1,500 grams of zinc, and we use its molar mass, which its molar mass is 65 grams in 1 mole, and it's 1 mole in 1 reaction, which when we look at this, zinc is going to be 23.08 reactions, which is what we thought because there's such a large difference between 200 grams and 1,500 grams. So we know that we have a reaction of 1.25 reactions. So what is our theoretical yield? Well, and remember, why are we trying to find the theoretical yield? Because it gave us the actual yield right there. That's what we found in the lab. The only thing to find percent yield is we need theoretical. So we go 1.25 reactions, and 1 reaction produces how much of our copper? Well, 1 mole. And then we look at 1 mole of copper produces, it's right around, its molar mass is 63.5 grams. So when we're looking at this, our theoretical yield is 79.4 grams. Well, to find our percent yield, there's our theoretical, there's our actual. So all we do is 70 divided by 79.4 grams times 100, and that'll give us a percent yield of right around 88.2% in that reaction. Let's look at another example. So when we're looking at this, we can go ahead and say that the combustion of propane, C3H8, is determined to produce 93% of the expected carbon dioxide. What mass of carbon dioxide is produced when 200 grams of propane is combusted in 100 kilograms of oxygen? So when we're looking at this, what we can do is we know that it has a 93% yield. So we have our percent yield. Since we have the mass of our reactants, we can always find the mass of the product, which is our theoretical yield. So it says, what is the mass of carbon dioxide produced? That's what's actually produced. In this one, it's a little bit different. We're looking for our actual yield. So in doing this, we have to calculate our theoretical yield. Now, one thing that we can pay attention to here, that's kilograms. Okay, not grams. So it's a big difference. So in this case, what we'll have is that's going to be 100,000 grams of O2. Now, comparing 200 grams to 100,000 grams, what's going to be your excess reactant? 100,000 grams. What's going to be your limiting reactant? 200 grams of propane. So sometimes, like in the previous problem, they're a little bit exaggerated where it's 200 and 1,500. Here, when we're talking about in this example, it's 200 grams to 100,000 grams. That's a lot of oxygen, no matter what mole ratio it is. So we know that the moles of our 200 grams of propane and the moles of propane, those are going to be our limiting reactant. So what we can do here is go ahead and work this out. So we have 200 grams of C3H8. Remember, whenever it says grams, what do we need? We need the molar mass, and we need to know how many moles are in a reaction. Well, how do we get that? Have to have a balanced chemical equation. So let's go ahead and do that. Our balanced chemical equation for this is that 1 mole of C3H8 reacts with 5 moles of O2 to produce 3 moles of CO2 plus 4 moles of H2O. Okay, there's our balanced chemical equation. So when we're looking at this, in 1 mole of C3H8 in 1 reaction. So remember, it said grams, so what do we need? We need the molar mass. The molar mass of C3H8 is right around 44 grams. So 44 grams in 1 mole, and then 1 mole in 1 reaction. And we see that it'll produce 4.54 reactions. Okay, and when we're looking at this, we have 4.54 reactions, and in 1 reaction, we know that we're solving for the carbon dioxide. So in 1 reaction, you have 3 moles of carbon dioxide. And what we see is that, take it to grams, 1 mole is in carbon dioxide is right around 44. Scoot that over so you can kind of see it a little better. And so we multiply this out and we'll produce a theoretical yield of right around 303.6 grams of CO2. And so when we're looking at this, 303 grams of CO2, we have a 93% yield. Well, let's look at our equation. Percent yield, our percent, will equal 100 times our actual all over our theoretical. Okay, so when we're doing this, how do we solve for our actual yield? Well, the first thing we can do is take our percent and divide by 100, and we'll get 0.93 equals our actual all over our theoretical. And to find our actual, we just multiply that by our theoretical. So our actual is going to equal 303.6 grams times 0.93, and that will give us an actual yield. If we start with that much of our reaction, it'll give us an actual yield of right around 282.3 grams of CO2.